Good morning, everyone. My name is Wongun from Hanyang University in South Korea. It's a great pleasure to present our work at the USENIX ATC. Today, I'm going to introduce a new SQLite journaling mode. It's called WALDIO. What we are trying to address two things in this work. One, solve journaling of journal anomaly problem. Two, improve SQLite performance. This is joint work with Keonwoo, Hankeun, Wook-Hee, and Professor Youjip and Professor Beomseok. This is the outline of the presentation. SQLite is in-process library and a transactional SQL database engine. It is known as the database for Android, iOS, and Tizen, and it is also used by many desktop applications. You will be surprised to know how frequently SQLite is used. It's not just used for database, but also used for storing all kinds of temporary data. As a result, SQLite is responsible for 70% of the iOS on Android platform. Suppose we are typing in hi on an app, then SQLite is called to write 2 characters, and 2 characters of SQLite create 40 kilobytes of write to the storage. It is because ext4 file system journals SQLite journal file. This is called journaling of journal anomaly. In more detail, here we show the insert operation on SQLite. When you insert one record to a database, SQLite calls 5 write calls and 4 after async for database and SQLite journal file. This is how ext4 file system works. When you write data in ordered mode, ext4 first write data and write metadata to journal area. Here we show what happens when SQLite and ext4 file system work together. When SQLite calls after async, ext4 writes the corresponding data and journal to storage. For each after async calls, ext4 writes a huge amount to write in file system journal area for the SQLite journal file. In the beginning, we start with 2 bytes, but in the end, 40 kilobytes is written to the storage. This is observed on all journaling modes of SQLite. Such I/O traffic is considered bad for overall performance. We reviewed the ways to write in file system, hoping to get insights on solving journaling of journal anomaly. There are 2 types of write in ext4 file system: allocating write and non-allocating write. Metadata is updated in allocating write, and non-allocating write does not update import metadata. This is I/O path for writing 4 kilobytes using buffered I/O with fsync to the storage. In both allocating and non-allocating write, file system journals updated metadata of the file. After async in allocating write is the same as fsync case. But if there is no allocated blocks, the ext4 file system only writes data blocks. Buffered I/O write instead page cache is involved. Direct I/O, on the other hand, transfer data from user space memory to storage. However, one important constraint is that direct I/O operation fails when I/O size is not sector aligned. Benefit of using direct I/O is observed when we use non-allocating write. Direct I/O does not accompany file system journaling. After analyzing the I/O behavior, we found that buffered write followed by after async and direct I/O in non-allocating write shows the same behavior. In both cases, ext4 does not accompany file system journaling. By analyzing the I/O behavior, we found the important key to solve the journaling of journal anomaly. We decided to use direct I/O for SQLite to remove ext4 journaling. Using direct I/O write in SQLite raw commit is a great idea, but it's not all that simple. While trying to use direct I/O based war mode in SQLite, we faced three issues. First, we have to avoid the metadata update in SQLite log commit. Log commit operation in SQLite use allocating buffered write. In order to avoid updating metadata in commit operation, we need to make it non-allocating direct I/O write. Second issue, we are faced with making the SQLite I/O size direct I/O compatible and block device friendly. The final issue is to make direct I/O write more efficient and flash memory friendly. Each layer in the I/O stack, such as DBMS, Filesystem, and block device layer, aggregates the I/Os on its own way to remove the I/O bottleneck. Otherwise, in SQLite, the individual row commit operations are separately issued to the storage device. We have to make writing direct I/O more efficient to reduce writing overhead. Okay, let's address each issue one by one. The solution to the first issue is free allocation with explicit journaling and using non-allocating direct I/O in war file. In war mode. We use the fallocate function to pre-allocate a certain amount of blocks for war file and initialize all allocated blocks, and then we explicitly call the fdasync to keep metadata in file system journal. This allows us to recover from the system crash. Using fallocate crashes another problem. When we call fallocate, it returns uninitialized blocks to protect stale contents remains on sectors of the flash storage. When SQLite writes a block for the first time, initialized flag is set. But when system is crashed before calling fsync, OS loses initialized flag state, and any attempts to read allocated blocks will return all zeros. So pre-allocation should return the initialized blocks without exposing stale contents. We saw three approaches to solve the problem of uninitialized block and stale contents on flash storage. First approach is to zero fill, but this operation unfortunately accompanies huge I/O overhead. So we modified the fallocate function in the second and third approach to allocate blocks with the initialized flag set, and we also used discard or trim command in flash storage to avoid exposing stale contents. Here we briefly explain how discard or trim command works when discard or trim command is issued with number of LBAs. It asks the flash storage to remove the mapping table entries for respective blocks. So with discarded or trimmed block, stale data is protected from inappropriate attempts to read. In the second approach, we mounted the file system with discard option. When 5 blocks are deallocated with discard mount option, file system issues discard command to erase them, so new allocated blocks are always free from exposing stale contents. In the third approach, the 5 blocks are unmapped when they are allocated. As I mentioned before, we modified the fallocate function to allocate blocks with the initialized flag set, and to issue discard or trim command to corresponding flash storage sectors. In this way, we can protect the stale data too. So after implementing all three schemes in our test platform, we decided to use the third approach with a trim command on eMMC. Second issue we talked about is making the SQLite I/O size direct I/O compatible and block device friendly. We examined the direct I/O write performance on Galaxy S5. We observed that larger degree of performance improvement when the I/O size is aligned with file system block size or NAND flash page size. This simple experiment provides an important direction for our optimization effort, leading us to align the I/O with multiple 4 and 8 kilobyte. But the problem is that in SQLite, neither the read log nor the undo log structures are comparable with direct I/O, and they are not sector and block size aligned also. In order to solve the problem, we implemented header embedding scheme in the read log structure. We placed frame header at the end of a word frame. The final issue we are going to address is making direct I/O write more efficient as flash memory friendly. In buffered I/O, OS aggregates the I/Os on its own way to flash them in large chunks to reduce I/O bottleneck. Otherwise, in SQLite, the individual log commit operations are separately issued to the storage device. We developed group synchronization to reduce the synchronization overhead. In group synchronization, we employ frame buffer and grouping interval. All log records which have been written during a grouping interval are maintained at the frame buffer. SQLite flashes frame buffer when the grouping time interval expires or when the frame buffer is full. The benefit of group synchronization is reducing the overhead for synchronizing, and it aligns the I/O with NAND flash page size. We add group synchronization feature for the enhancement in performance. In this feature, the frame buffer size is set to 16 kilobyte with 2 millisecond grouping interval. Now, we discuss durability issue. Using buffered I/O in original SQLite synchronizes data to page cache when calling write function. And data is synchronized to storage surface by calling fsync or fdatasync. When you call direct I/O write, the data reaches only to the write back cache of the flash storage. But to guarantee durability, the log in the cache should be written to the storage surface. Suppose the data is on the write back cache and the system is crashed, then the data in the cache lost. To make data durable, we use 3 types of direct I/O for our new journaling mode. First, we use direct I/O with SQLite full synchronization option. Direct I/O write only writes to the write back cache of the flash storage. Full sync option in SQLite calls fsync or fdatasync after each log commit. So writing data is flashed to the storage surface. Second, we implement persistent direct I/O, or in short PDIO, for better performance. PDIO follows a reliable write command stated in eMMC standard. Writing direct I/O with PDIO writes the log directly to the storage surface, bypassing not only the buffer cache but also write back cache of the flash storage. Persistent direct I/O eliminates the overhead in calling fdatasync. It shows better performance than direct I/O with full sync option. Third optimization assumes non-removable battery in the smartphone. Such case potentially makes direct I/O write a persistent write even without full sync option of SQLite. The logs in the write back cache of the storage can survive the warm failure as long as the power supply leaves some slack on flash storage. We harmonized all of the features mentioned to form a new SQLite journaling mode and named it WALDIO. And we implemented WALDIO in the recent smartphone model Samsung Galaxy S5. This figure shows I/O trace of 10 insert operations in WAL mode and in WALDIO mode. The radius of each circle denotes the size of an I/O. In WAL mode, each log commit writes 8 kilobytes to SQLite journal file and writes 20 kilobytes on file system journaling. In WAL mode, Each log commit yields just 4 kilobyte I/O. As shown in the graph, there is no file system journaling nor non-optimized data writing. WALDIO successfully eliminates the file system journaling overheads since the logo is committed with direct I/O, and WALDIO successfully optimizes writing data since the frame header is embedded with the database page. Okay. We performed each of insert, update, delete operation 1,000 times and measure the performance. We categorized them into 5 groups: stock SQLite, LSMBBT, WALDIO with full sync option, WALDIO with persistent direct I/O, and WALDIO with normal sync option. Here we examined the performance of WALDIO with group synchronization. Compared to stack war mode, WALDIO persistent direct I/O obtains 2.2 times better performance in the absence of group synchronization. When you use group synchronization, WALDIO persistent direct I/O shows 5 times better performance than the stack war mode and 2.7 times better performance compared to LSMBBT. When the battery of a smartphone is not removable or stored data is considered as not significant, we can use WALDIO normal sync. Normal sync case shows 4 times better performance than LSMBBT and 7.4 times better performance than war mode. The performance of delete and update operations are not different from insert operation. Next, we examine the total I/O volume. Compared to war mode, the total volume decreases to 1/6. The volume decreased from 29 megabyte to 4.6 megabyte. Since erase and write cycle of the flash storage is critical to lifespan of smartphone, using our scheme significantly improves the lifespan of the device. Here is the summary of our paper. We developed pre-allocation with explicit journaling, header embedding, and group synchronization. This implementation allows SQLite to use direct I/O semantics without having to compromising file system integrity and to optimize the performance of SQLite for flash storage. We integrated all the changes to form a new SQLite journal mode, and we named it as WALDIO. Compared to WAL in stock SQLite, WALDIO shows 5 times better performance. Moreover, WALDIO with the normal sync option shows 7.4 times better performance compared to stock WAL mode. In this work, we successfully resolved the journaling of journal anomaly. As a result, we achieved significant performance improvements by optimizing the I/O stack and SQLite. Thank you.
I'll start with one. So in previous work from your group, you have other solutions where you change the B3 operations inside the SQL, right? Can you comment on comparisons between this work versus other works that solve journaling of journal anomaly?
Yeah. Actually, this technical issue is studied by our second author. So, may I answer to you after? Talk with second author. Yeah, thank you.
This work seems to suggest that for sort of infrastructure programs like SQLite, it may almost make sense to have a lower level file system interface than what we normally have. Do you have any thoughts on in that direction? In other words, how much of this is due to, using higher level file system features like non-aligned partial rights and so on, that, go away when you you're essentially stripping out some of the functionality of the file system in the modes that you're providing.
Sorry, but I
To
have
refresh,
yeah,
I'll take this offline.
should we have
Yeah,
a
yeah.
specialized file
please
system
mail me.
for
Sorry. Okay.
Yes,
Well,
should
I
we,
think that's the
should we
question.
have, or a specialized, do you think we need a specialized low-level file interface for SQLite,
Yeah.
Postgres, key value stores, all these non-user applications?
Okay. I think I have not enough answer right now, but I will send it to you after more searching.
Thank you.
Thank you.